For centuries, humanity has gazed upward at the vast cosmos, endlessly seeking to unravel the fundamental laws that govern our entire universe and everything within it. This profound and timeless quest has ultimately led us to the remarkable discovery of four fundamental forces of nature that underpin all physical interactions. First among them is gravity, the universal force that pulls planets into stable orbits around stars, keeps our feet firmly anchored to the ground, and shapes the grand large-scale structure of the entire cosmos, from galaxy clusters to the cosmic web. Then there is electromagnetism, the versatile force responsible for producing light, generating electricity, creating magnetism, binding atoms together into complex molecules, and ultimately powering the technologies of our modern industrialized world. The strong nuclear force stands as the most powerful of all these forces, relentlessly holding the atomic nuclei together by overcoming the intense electromagnetic repulsion between the positively charged protons crammed within. And finally, the weak nuclear force governs processes like radioactive decay and the stellar fusion reactions that power the sun, enabling the transformation of one type of subatomic particle into another through delicate interactions. For decades now, physicists around the world have pursued a unified theory, a single elegant framework capable of describing all these diverse forces in harmony. A major milestone in this pursuit was the development of the Standard Model of particle physics. The Standard Model successfully unified electromagnetism with the weak nuclear force into what is known as the electroweak force, and it also elegantly incorporated the strong nuclear force into its comprehensive structure. This groundbreaking model meticulously describes the fundamental particles, such as quarks and leptons, along with their interactions mediated by force-carrying bosons like gluons, photons, W and Z bosons. A pivotal component of the Standard Model is the Higgs boson, famously dubbed the God particle, which interacts with other particles through the Higgs field to endow them with their essential mass properties. The monumental discovery of the Higgs boson in 2012 at the CERN Large Hadron Collider was a resounding triumph, providing crucial experimental confirmation of a key cornerstone in the Standard Model's intricate puzzle. Despite all its remarkable successes, the Standard Model remains notably incomplete, as it entirely fails to incorporate gravity, the dominant force that governs the universe on its vastest cosmic scales. Einstein's general relativity brilliantly describes gravity not as a force, but as the smooth curvature of space-time caused by the presence of mass and energy, envisioning it as a continuous, flowing fabric. In stark contrast, the quantum world, where the other three forces operate, is inherently discrete, probabilistic, and filled with chaotic uncertainty, governed by the principles of quantum mechanics. Reconciling these two profoundly different descriptions of physical reality, one smooth and deterministic, the other jagged and probabilistic, stands as the central, defining challenge in humanity's search for a theory of everything. This deep-seated fundamental incompatibility starkly underscores the urgent need for innovative theoretical frameworks that can successfully bridge the vast gap between the macroscopic world of gravity and the microscopic quantum realms. One of the foremost leading contenders in this quest is string theory, which boldly proposes that the fundamental particles we observe are not truly point-like, but instead manifestations of tiny, one-dimensional vibrating strings. These minuscule strings, on the order of the Planck length, vibrate in various distinct modes, with each unique vibrational pattern corresponding to a different type of particle, crucially including the graviton as the hypothetical carrier of gravity. To make this work, string theory necessitates extra spatial dimensions beyond the familiar three we perceive, which are compactified and curled up at scales so extraordinarily small that they remain undetectable by current experiments. Another highly promising candidate is loop quantum gravity, a theoretical approach that boldly attempts to quantize the fabric of space-time itself at the most fundamental level. Rather than a smooth continuum, this theory envisions space-time as an intricate network composed of discrete quantum loops, akin to the indivisible atoms of space existing at the minuscule Planck scale of 10 to the minus 35 meters. Thus, space and time are not continuous flows, but granular structures, much like how ordinary matter is ultimately composed of discrete atoms, challenging our intuitive notions of reality. Loop quantum gravity provides a natural framework in which gravity emerges organically from the intrinsic quantum properties and geometric interactions of these fundamental loops. The relentless search for a theory of everything remains one of humanity's most ambitious and intellectually demanding scientific endeavors, continually pushing the outermost boundaries of our understanding of nature. Success in this quest promises to unlock the universe's deepest secrets, illuminating phenomena from the explosive birth of the universe in the Big Bang to the enigmatic hearts of black holes. Discovering such a unified theory would not only revolutionize the field of physics, but also profoundly and irrevocably transform our fundamental perception of reality itself. Just imagine a single, profoundly elegant equation or framework that seamlessly explains everything, from the tiniest subatomic particles buzzing with quantum energy to the colossal galaxies spanning billions of light years. Though the journey ahead is undeniably long and fraught with immense challenges, the potential rewards are truly immeasurable, offering humanity a complete, awe-inspiring picture of our vast and mysterious universe.